Hey, Benjamin. All right, it's 4 o'clock, so let's go ahead and get started today. Good afternoon, everyone. How's everyone doing today? Good, good. I'm good. Still a bit tired. Recovering from the second dose of the vaccine, but doing good otherwise. Okay, so today we're going to do Ansys activity 4, and so I went ahead and kind of did the activity before the class today, just so you can kind of see where we're going. Okay, and so in Ansys activity 4, we're going to be doing this. So we're basically simulating a car crash, right? And so we're going to be running a simulation where a car basically runs headfirst into a concrete wall, and then we're going to watch and see how it deforms. Okay. And so, this is a great example of, why you would want finite elements, right? And so like if you're designing like an automobile, you work for Toyota or something like that, right? It's really expensive to take a car and to run it into a wall just to run some tests, right? And so ideally what you would want is you would want to do most of your design, most of your modifications digitally like this, right? And so you would run the simulation, you would see how the car behaves after striking the wall. You would make your modifications to either lessen the stress or to distribute that force somewhere else. And then only until you're very confident about your design that you would actually go and actually destroy a car, just for testing purposes. Okay. And so, we're going to be using a whole new element to Ansys today. And so up to this point, we've only just been doing static simulations, but today we're going to be doing dynamic ones. Okay. All right, and so if you want to follow along, you're definitely welcome to do so. So I would definitely start up Ansys Workbench right now, because it's going to take a while. And just like I mentioned on Tuesday, that this activity is probably the most computationally demanding of all the activities that we're going to do this semester. And so it's a lot more than just solving for one finite element solution here. And so the way unsteady problems like this works is that we basically solve a finite element problem at each of the different time steps, right? And so we're going to be solving, this for this solution in this case for about 0.75 milliseconds. And so the time in between 0 to 0.75, that's broken up into lots of different, little time steps. And so think of that like when you're looking at the video quality for like a YouTube video or something like that, right? When you see a video, what you're really viewing is a series of still frames that are just played really, really fast, right? And so if you see a video that's 30 FPS, that's 30 frames per second. And so every second you're basically viewing 30 frames, and they're all just being shown to you very, very quickly, right? And so unsteady simulations in finite elements work the same way. And so for unsteady finite element simulations, you have to solve a separate finite element problem, for each frame of the video that you want to produce, right? And so because of that, instead of just doing just one finite element calculation, you're going to be doing lots and lots of them here. And so, if you have confidence in your computer, definitely, you can run it here. But if you, think it might be a little bit slow on your computer, then you can run it on the virtual computing labs, and it should run great there. Okay. All right. So let me go ahead and pause this video, and let's go ahead and take this activity from the top. And then while I'm kind of setting things up, are there any questions that I can answer about anything before we get started? Okay, right. And so, at any time, you're definitely welcome to, ask questions at any time, and I'm always happy to answer them. Okay, and so the geometry for this activity can be found on the Canvas site. So let's go there first, right? And so if you go to our class, and let's go to assignments, and we see Ansys activity 4. Okay. And so from this page, you can see that, there's 2 files for you. And so the first file is the PDF. And so just like, all our previous activities, you can find the instructions, and screenshots for everything in this PDF, right? And so you can definitely follow along in that PDF. But then the CAD file that you actually need is going to be this one right here, okay? And so you can see it's a step file, and I call it car crash analysis.step, right? And so if you're going to follow along, definitely, download this file. And then let's open it up in Ansys after that. Okay, and so now that you've downloaded the file, and now that you're here in Ansys Workbench, we need to define the type of physics that we're solving, right? And so traditionally, for our first 3 activities, we've used this this analysis tool right here, which is static structural, right? So that's a structural simulation that's static, and so it doesn't move. But for this case, since it's a dynamic situation where the car is going to be hitting, or impacting the wall, we need to use a different set of physics for this one, and it's going to be explicit dynamics, okay? And so you're going to take explicit dynamics, and you're going to click and drag it into the center of the workspace right here, just like we always do, okay? And you'll see that you've created basically an explicit dynamics object, which we'll use to, set up all of our simulations, okay? All right, and so the first thing we need to do, just like we always do, is we need to load in the geometry, right? And so you want to right-click on geometry here in Explicit Dynamics, and then you're going to import your geometry, okay? And so you're going to click Browse, and then you're going to go to the location where you downloaded the file, right? And so you go ahead and highlight car crash analysis.step, okay? And then load that in, and then once you load that in and you see this green check mark, then you're good to go. All right, and so the next thing we're going to do is we're going to add material properties. And so, for this activity, we're going to assume our car is made of aluminum. And so we need to add aluminum into our workspace in order so that we can run the simulation with that. Okay. All right, so let's go ahead and double click engineering data, just like we always do. And you can see that right now we only have one material here for structural steel. Okay. And so to this, we need to add an aluminum. And normally we do it by creating our own custom material. But for this activity, just to kind of speed things up a little bit, we're going to use the built-in aluminum alloy that's in Ansys, right? And so to get that, you're going to click on Engineering Data Sources right here, okay? And so that's this button here with the little library of books. And then doing so, you're going to open up, a lot of windows. So it's kind of window, kind of a lot going on here. But the place where you want to look at is kind of this top. This should be this top middle window here for engineering data sources. Okay. So is everyone that's following along, are you able to get engineering data sources here with this list that I have here on the screen?
Yep.
Great. Great. Okay. And so and so you can see, from this engineering data sources, there's lots of different types of materials that you can go into, right? And so this is something that's updated with every version of Ansys. And so I think last year when I did this, the list didn't look like this, but we want to go into this list right here for general materials. Okay, so let's go ahead and double click general materials. And then give it a second. I think I accidentally closed that window. Let's see. It's always the issue. Okay, and so if you're not able to view the that window, you might have to click Reset Workspace, right? And so you're gonna click View, click Reset Workspace or Reset Window Layout. Let's do that. Oops. Okay. Right. And so if you have to reset it, you double click General Materials, and you should see this window in the middle here for outline of general materials. Okay. And so here's the list of all the general materials that you have available for you in Ansys, right? And so here, it's really general, and so you can put almost anything here. So you'll see air, and air seems like a strange material to have because you're not going to be building any structures out of air. But remember, Ansys is a general kind of finite element software, and so you can also do like fluid simulations, and you can do heat transfer as well. And so that's kind of why air is here. But yeah, you wouldn't use air for any kind of structural structure. Okay. All right, and so the one that we want to add here is called aluminum alloy, right? And so you can check the material properties here for aluminum alloy, and so you'll see it's very similar to the materials that we use in past activities. Okay. And then we want to add it, and then we want to add it to our workspace. And so we want to click this plus arrow right here next to aluminum alloy, right? All right. And so after you click that plus arrow, you should see this little book that appears here in the column next to it, and that tells you that we're going to be using aluminum alloy, and it's going to be available to us in this simulation. Okay. And so go ahead and click the plus sign next to aluminum alloy to add it. And I want to add one more material here as well, right? And so just kind of just for fun, at the end of the activity, we're going to run the car crash simulation and assume that our car is made of plastic, right? And so the type of plastic we're going to use is a polyethylene. And so let's go ahead and add that material as well. And so click the plus sign next to polyethylene, okay? And you should see a book next to that as well, right? And so if you go back to the original menu right here by clicking Engineering Data Sources, you should see we have three materials here. So we should have structural steel, which is the default material. We have aluminum alloy, which is the one we just added, and also polyethylene for plastic. Yep. Yeah, it's basically, yeah. It's if your car was made of the same material as a water bottle, and then that's basically what we're going to see. So it'll be a fun thing to see. Okay, so any questions on this so far? Okay. All right, and so now that we've added all the materials, we can go ahead and close our engineering data. Okay. And then we want to double click on model right here. Okay. And this is just like before, this is going to bring up Ansys Mechanical, where we're going to perform most of the simulation. Okay. And of course, it always takes a little bit of time, so let's wait for it a bit. Mine might be a little bit faster than your guys's too, because I was just running it earlier. So it's Ansys is already on kind of my my RAM. Okay, and so I'll give people a couple more minutes to load the Ansys Mechanical if you're still loading. Okay, but once you've loaded the Ansys Mechanical, you should see this, right? And you can see our CAD model consists of two separate parts. And so we have one part here, which is, the concrete wall, which is just a, just a steel slab. Okay. And then we have our car, or at least a very simplistic, very simplistic representation of the car right here. Okay. And if you, just like we saw in Ansys Activity 3, where we have two different parts, you can see, you can highlight them here. Okay. All right. And so if you've loaded up the geometry, let's go ahead and assign these material properties, right? And so if you click on the two parts here, you'll see that one part, the first one that you click here, that's the car itself, okay? And so the second part on the list, that's the wall. Okay? And so right now, this naming, these names are not particularly helpful, and so I'm going to go ahead and rename these. This is optional, but I'm going to go ahead and rename this. And so since this is the car, so I'll call this the car frame, okay? And since this one's the wall, I'm going to call this the wall, okay? And this is kind of just for my own, organization later, so I don't get confused between the parts. Okay, and so now let's go ahead and assign the material properties. And so the first thing we need to do is assign the material properties for the car frame, right? And so you see, right, if you click on car frame here on the top left, and then you go to the bottom left of the screen, you can see the material assignment for this right now is structural steel, which is the default, right? And so let's go ahead and change this to aluminum alloy, right? And so you can do that by clicking on this list right here and clicking on aluminum alloy, right? And now our car is made of aluminum. All right, and so now there's the wall. And so the wall, we don't really care about the wall too much. It has to be there because our car has to hit something. But besides that, we don't really care what it's made of. And so all it has to do basically is just to absorb the car's impact and just not move. And so, traditionally, a wall like this would be made of concrete. I think that's the first thing that people think of. But for this case, we can just leave it as structural steel, and that's fine. Right? And so structural steel is definitely strong enough to withstand a car hitting it, especially a plastic car. And so leaving it as structural steel is fine for this case. Okay.
My outline disappeared. How do I reset that?
Let's see. You mean this this
Yeah.
window right here? Let's see. So you have something like this.
It's just just the material, the model. It doesn't have anything on the left side.
Okay. Let's see. So there should be something like reset viewpoints. So you can probably do the same thing here. So we probably reset. Yeah. So if you go up to the upper right and you search reset, then you can click on home layout.reset layout, and then it should bring this back. Yeah.
Okay. Thank you.
Yep. Mm-hmm. All right. Question. So what units will we be working with in this activity? Yeah. Good question. So let's go ahead and set our units right now. And so the units we're going to be working with are going to be this first one here. So meters, kilogram, newtons, seconds, and volts. Yeah. Yes, we want to later on we're going to assign the velocity of the car in meters per second, and so having it in this unit system is most convenient. Mm-hmm. All right. Any other questions so far?
We didn't assign any material yet, did we?
We did. So for the car, we assigned it to be aluminum alloy, and so make sure the car is made of aluminum. And for the wall, it doesn't really matter. And so you can have structural steel, and that's fine for this case.
Okay, cool. Thank you.
Mm-hmm. All right. And so we need to do one more thing before we move on, and that's to define these contact regions, right? And so if you remember from Ansys Activity 3, whenever we have an assembly of parts within Ansys, we have to define how these different parts are going to interact with each other, right? And so in this case, we have two parts of our assembly. And so we have the car and we have the wall, right? And so, because they're, the CAD model, they're very close to each other. Ansys has gone and defined their relationship to be bonded, okay? And so right now the car is welded to the wall. And so we don't want that. And so what we want is we want the car to be able to strike the wall, and we want the car to be able to kind of bounce off the wall, okay? And so for this activity, we're going to eliminate this contact region in between them, right? And so, on the outline here, you should have, this just drop down menu for connections. And so let's go ahead and expand this, and then expand the list of contacts, right? And then if you click this contact region right here, you should see it's between the wall and the car. And so let's, in this case, we're just going to go ahead and delete it, because there's, we don't want these, this car to be sticking to this wall at all. And so they don't really have a relationship here. And so let's go ahead and right click that and delete. And then it's going to ask you if you're sure that you want to delete it. And I say yes. Okay. Right. And so once we do that, now the car and the wall have been unmated from each other. And so now the car can strike the wall, and it can bounce off, and it can do all kinds of crazy things. Okay. And so that's really important for this activity. And so if you don't do that, then we can assign a velocity to the car, but it's just not going to do anything because it's attached to the wall. Okay. And so we need to make sure that we've removed that connection between the wall and the car, so that we can actually see the car actually start to crumple. Okay. Okay. And so that's the connection, right? And so next thing we're going to need to do is we need to mesh this guy, right? And so we have two objects here, and so we're going to need to create both a method object and a sizing mesh object for each of those different things. Okay. All right, so let's go ahead, and just like we've done in the previous activities, let's go ahead and right-click Mesh, and then click Insert, and then go ahead and click Method. Okay. And then first, let's define things for the wall. Okay, and so for the geometry for the wall, I'm going to left-click the wall, and so it's all green. And then I'm going to click Apply in the bottom left corner of the screen. Okay. Right, and so now we can define the meshing properties or the meshing method for the wall itself. Okay. All right. And so, just like we've done in the past, you can go ahead and select the shapes for this. So you can either pick tetrahedrons or hexahedrons, or the stuff. But again, the wall doesn't really matter too much, and so we're just going to leave it as is in automatic. Okay. But one thing that we do need to do for this simulation, because this is a dynamic simulation, is we need to change the element order to linear. Okay. Which is counterproductive to to everything that we've been discussing since Tuesday, where even though this is a dynamic simulation, it's still structural in its nature, because the car is going to structurally deform. And so if you remember what we talked about on Tuesday, we talked about the issue of shear blocking, which is a dangerous thing, where if you have a linear finite elements, then you could have the whole system just kind of lock up, right? And so that concern is still there. But right now, because we're running a dynamic simulation, the problem we're going to run into instead is that if we use quadratic elements, then the computational cost of the simulation just becomes a little bit too much to bear. And so whenever you're running a dynamic simulation like this, you need to set the element order to linear. Right? And so it's not ideal, because ideally you would want to use quadratic elements for this. But just because we're hamstrung by running a dynamic simulation, we have to change this element order to linear. Okay. Okay. And so that's the method for the wall. And so let's go ahead and add a sizing object. Okay. Right. And so now we added a sizing object to the wall. Right. And so I'll wait a little bit before we change this. And so let's go ahead and see how the mesh turns out before we do that. Right? But before we do that, let's go ahead and do the same things for the car. Oh, question?
So wouldn't it be possible to just make the mesh coarser or something while keeping it quadratic?
Yeah.
So that it could go around?
Yeah, no, that's a great question. And so so that's exactly what we talked about on Tuesday, where you can either do both. So you can either do you can either increase the element order to quadratic, or you can make the mesh finer. But the thing is, with dynamic simulations, there's a lot more going on underneath the hood, in terms of calculations. And so for when you do quadratic elements, it makes the dynamic simulation a lot more complicated than if it were just a static one. And so I know that's not the best explanation, just because we're not going over any of the theory for dynamic finite elements in this class. It's something I would love to do, but it's a little bit beyond than just an introductory course. But once you start getting into dynamic stuff, having a quadratic element really makes things a lot more complicated. And I've tried this activity with quadratics before, and then like every single time it kind of complains. And so I'm not sure if it's strictly a limitation of the student version where they just make it a hard stop where it's like you can't do dynamics with quadratics. But I do know that when you're implementing the code, it does add a lot more cost compared to just just a static situation of just doing linear and quadratic. And so yeah, the dynamics it adds a lot of complexity to the problem, and the quadratics kind of takes it up just to a level that's a little bit too much for the student version. Yeah, great question though. Okay, and so let's go ahead and make method objects and sizing objects for the car as well, right? Okay, and so I'm going to change it. I'm going to change the car's elements to make it linear finite elements. Right, and let's go ahead and add a sizing object to the car as well. Okay, oops. Okay, and so I'll adjust the sizes in a bit, but first let's go ahead and run this mesh, and then let's see how the meshes turn out. Right, and so after you put in the automatic method objects and the body sizing objects, go ahead and right-click mesh here and click generate mesh. Okay, and then with the default settings, you should get a mesh that looks something like this. Okay. All right, so is everyone able to get a mesh that looks something kind of like this? Right, great. Yeah, it's yeah. I mean, whenever you have multiple objects, it's always kind of slow. So it's yeah, it's tough. Okay. And so I'll wait a little bit for people who are still meshing, but we're going to mesh it again. So don't worry too much. Okay. All right. And so let's look at the mesh that was created. Okay. Our question. So what was done to get the body interactions folder underneath the connections folder? This was kind of already automatically generated. And so if yours if yours isn't there, then I wouldn't worry about it too much. I'm actually not sure what this body interaction does. And so mine, all it does is says that it's frictionless, which is what we want. Like we don't really want any interaction. So if you don't have body interactions, don't worry about it too much, because we don't really want the bodies to be interacting in any kind of special way. Yeah. Mm-hmm. Okay. All right. And so let's look at this mesh right here, and let's see how we can adjust it based on what we're interested in the simulation. Right. And so if you kind of remember from the from the animation I was showing at the beginning of lecture, what we're primarily interested in is how the car is going to react to how it's after it hits the wall, right? We don't really care what the wall was doing, because the wall was just there as just kind of a as kind of a placeholder. The car just has to hit something. And so looking at this mesh in the wall, you can see that we have a fairly refined mesh here, and so we have a lot of elements going on. And so this is kind of a waste, because since we don't really care what's going on in the wall, we can afford to coarsen up this mesh quite a bit and still get simulation results that we're happy with, right? And so let's go ahead and adjust the sizing for this wall so it doesn't look as fine. Okay. All right, and so you can see that the default mesh size for the wall right now is 0.0175 basically, right? And so let's go ahead and increase this by a factor of 10. And so let's make the 0.175, okay? And then let's generate our mesh again, and let's see what that looks like. Whoa, okay, so that's a little bit too much. And so you can see now that we've kind of made this mesh a little bit too blocky. And so let's tone it down a little bit. And so let's make the mesh sizing for the wall equal to 0.1. Okay, and so now we have like a chocolate bar for the wall, and this is fine. So this will be perfect, and so this will give us a good place for the car to hit to. Okay, and we're not wasting a ton of elements here. Okay, we should have checked the statistics beforehand, but it's okay. Okay, okay, and so now that we've coarsened up the mesh in the wall. Let's go ahead and refine the mesh in the car itself, right? And so we really need to do this because remember, since we're using linear finite elements, we're really in danger here of shear locking, right? And so we want to make sure that our mesh on the car is fine enough such that we kind of get around that effect, okay? And so you can see right now the default size for this is 0.0175, right? And so let's go ahead and refine this a bit. And so instead of 0.0175, let's make it 0.01. Okay. All right, let's go ahead and generate the mesh, and let's see what we get from that. Okay. And so you can see here now that we refined this mesh quite a bit. Okay. And so it looks a little bit better. And so let's go ahead and refine this a little bit more. And so let me cut this in half. So let me, instead of 0.01, let's do 0.005. Okay, and let's do that. Right, so let's go ahead and right click, generate the mesh again. Okay.
Does it matter that sometimes it shows up purple, like, or is that just the program itself?
Does it say failed mesh anywhere? For the
no,
purple?
it's just like sometimes it, instead of it being gray how it is right now, it'll be purple with the mesh.
Oh, I think it's okay. And so probably what's happening is you might have something selected up here or something like that, or you know it might just be a rendering thing. So yeah, I wouldn't worry about it too much. Yeah.
Okay.
Yeah.
It does that for me when it's generating the mesh, and then when it's done, it goes back to gray.
Okay. Okay. Oh yeah. So probably if it's still generating the mesh, yeah, it might be purple because it's you know it's still thinking. Yeah. And then sometimes there might be some rendering issues where it kind of gets stuck like that and the color kind of persists. But yeah, as long as it doesn't return any errors, it should be okay. Okay. And so I think this is actually finer than what I ran it with earlier. And so let me actually coarsen this up a little bit because our element count here is pushing a little bit high. And so you can see here we have 28,000 elements. And so let me go ahead and coarsen this up to 0.00, let's do 6.5. And so you don't have to do exactly the same as me. And so you know you can choose a mesh on your own. But I will say that this particular activity is pretty sensitive to the mesh, and so depending on you might end up with pretty different results in the end, depending on what your mesh is. But for me, just to make sure that we're not sitting here for like 20 minutes waiting for the simulation to run, I'm going to run with a mesh of 0.0065 for the car, right? And the number of elements that it gave me was about 16,000, right? And so you don't have to do this one, but if you have faith in your computer, you can push this a little bit more. But that's the one I'm going to run for this activity. Okay, so any questions so far? Okay. All right, and so that's the meshing, and so that's problem 1 on the homework. And so if you want to kind of get a jump start on the activity, you can go ahead and take screenshots of this. Because I think the only thing I asked for problem 1 is just a screenshot of your final mesh, okay, as well as a few sentences to kind of describe what you're doing. Okay. And so now that we have our mesh, let's go ahead and start applying our boundary conditions. Right? Okay. And so this case is going to be a little bit unique compared to our past cases because, for all our previous finite element simulations, we've had to apply both loads and constraints, right? And so loads being things like forces and pressures, and those are going to cause our simulation to deform. And constraints are obviously, things that prevent your body from moving. Right? But for a dynamic simulation, it's you don't really need both. And in particular, you don't really need loads because the load that we're going to apply is going to be from the velocity of the car that we plunge into the wall, right? But we do need to constrain this, and so we need to make sure that when this car hits this wall, they all don't just go off together and making their way downtown at all. Right? All right. So first thing we're going to do is we're going to constrain the wall, and so we're going to right-click on Explicit Dynamics A5, and then we're going to apply a fixed support. Right? And so the fixed support we're going to apply on the wall. Right? So let's go ahead and click Fixed Support. Okay. And then make sure that you're on Face Select mode, and so you're going to change from Body Select mode to Face. And then we're going to select all the outer surfaces of this wall right here, right? And so you might need to use a Control-Click in order to select all of them, okay? And so you want to basically fix it so that the outer edges of the wall are not going to move. Right? All right, so let's go ahead and apply that. Okay, and now the wall here is going to be fixed. And so this is basically to simulate the situation where this wall is going to be part of a much bigger one, right? Which is usually the case, right? And so that's how we're going to fix the wall. You want to be careful here because you don't want to fix the entire wall itself, because we don't want to fix this surface here where it's going to make contact with the car, right? And so if we do that, some weird stuff is going to happen in the simulation. And so you want to make sure that this surface here, the one that's actually going to be contacting the car, this one is still free, but we constrain everything around it, just that the wall itself doesn't move. Okay, but we want to keep this surface free so that the car can hit it and it can kind of bounce off that. Right? And so it's a subtle point on where you want to fix the simulation, but it's kind of an important one because it's otherwise some weird stuff is going to happen in the simulation. Okay. Okay, and so that's our fix support. And so now our wall is fixed, and so we don't have to worry about that moving around. And so the next thing we're going to do is we're going to constrain the motion of the car a little bit. Okay, and so the car, of course, is going to be free to move in the X direction. And so you can see if I rotate here, you can see the X direction is kind of the forward direction of the car, right? And so we want to leave that direction free so that the car can move that way. But what we want to do is we want to constrain the motion in the Y direction right here. Right? And so what that's going to do is it's basically going to prevent the car from displacing into the road, right? Because in reality, this car is sitting on top of a road, and so we want to make it so that the car, doesn't clip into the ground, right? And so to do that, we're going to apply a new kind of constraint, which is a displacement constraint. Right? And so with displacement constraints, we're going to be able to constrain just a certain component of the displacement instead of the entire thing being fixed, right? Oops, mouse slipped. Let me go ahead and delete that. Right, so I'm going to insert displacement. Okay, and so you can see, after we create the displacement constraint in the bottom left of the screen, we can prescribe the X, Y, and Z components of the displacement. Okay, and so right now all of them are free because we haven't constrained anything. But let's go ahead and constrain the Y direction of the displacement, and let's set the Y direction to 0. Okay, and so what that says is that whatever we choose for the for the geometry here cannot displace in the Y direction. Okay. And so it's going to be free to displace in the X and Z directions, but in Y direction, it can't displace. Right? And so you can almost think of this as the same thing as a roller support, right? And so if you think back to our roller supports, our roller supports were able to, constrain, displacement in one direction, but leaving the other direction free. And so this is kind of the same thing as that, right?
Professor?
Yeah.
Would it be possible to do a half constraint basically where it's, able to, if it crashes into an object that's angled and then, jumps up a bit, would that be?
Yeah.
Just the ground, yeah.
Yeah, I think it is. I think the way you do that is you might have to do like a greater than sign here or something like that. I haven't actually tried it in Ansys before, but it's that is a very common thing. And so especially for a situation like this, like you would want to have the car be free to displace upwards, to crash and go upwards a little bit, but we just don't want it to go down. And so I think the way I don't want to say because I haven't actually tried it out in Ansys, but I think the way is like some kind of greater than sign, to make it so that it can go one direction but not the other one. But I think you have to input some kind of function in here to do that. I just haven't tried it before in Ansys. Yeah. Okay, and so the geometry that we're going to apply for this constraint here is going to be the entire lower edge of the car, right? And so it's going to be a little bit hard to click because it's kind of such a thin surface. But I want you guys to constrain basically, oops, not that one. All of these kind of thin bottom things here. And so in the end, it should look like, the entire bottom edge of the frame here should be constrained. Okay. And so that's kind of to emulate the fact that, this car is on wheels and the wheels are going to be contacting the ground. Okay. And so we don't actually have the wheels here. And so we're going to do the next closest thing to the wheels, which is just the bottom surface of the car, right? And so you might have to zoom in, you might have to mouse around in order to click the right surfaces, but yeah, go ahead and make sure that you're clicking the right ones and you apply that geometry here. Okay. All right, and so once you do that, then the bottom surface of the car will be constrained, and then so it doesn't displace in the y direction, and then of course the size of the wall are constrained so that our wall itself doesn't move. Okay. All right. Any questions on this so far? Okay. All right. And so that's our constraints here. So all that is, the same so far mostly as our static simulations. And so now we're going to add something new. Okay. And so since we're doing a time-dependent simulation, we need to add a initial condition. Okay. And so initial condition, just like the name kind of implies, this is, it defines what each of the objects are going to be doing at the beginning of the simulation. Okay. And so since this simulation is going to progress in time, we need to define, what everyone's doing at the beginning. Right? And so we have two objects here, and so we need to define what each of the objects are going to do. Right? And so let's start with the wall. Right? And so the wall at the beginning of the simulation is going to be sitting there, and then at the end of the simulation, it's going to be sitting there. Right? And so the wall is going to do nothing but just sit. Right? And so that's perfect. And so we don't actually need to prescribe any initial condition for the wall, because it's already doing what we want it to do, which is just sit there and just get hit and then react to it. Right? And so we don't have to do anything for the wall, but we do have to add an initial condition for the car itself, right? Because we want to prescribe the initial condition such that the car is going to be going towards the wall with some velocity, right? Right. And so let's go ahead and right-click initial conditions, and then you're going to insert a velocity initial condition here. Okay. And so that's going to help us, that's going to allow us to prescribe a velocity for the car at the beginning of the simulation. Right? Okay, and so let's go ahead and click velocity, and you'll see a new window pop up. And then just like we usually do for the different parts of Ansys, we need to specify the geometry that we're going to be acting on. And so the geometry that we're going to apply the initial condition on is on the car. And so let's go ahead and select the car. Go ahead and hit apply right here. Okay. And now we want to specify a velocity in the -x direction, right? And so if you look at our coordinate axis here on the bottom right, you can see that the positive x direction is going away from the wall, but the negative x direction is going into the wall. And so we want to specify a velocity in that negative x direction. All right. And so just like we usually do with our loads, we can go ahead and define our velocity here in terms of components. And so that will allow us to supply the x, y, and z components of the velocity. And so for this simulation, we're going to assume that the car is going faster than a bullet, okay, just for kind of maximum crash potential. And so I'm going to set the x velocity to -150 meters per second. Yeah, it's going fast. It's a very, very fast car. Yeah. And so of course, you can change this velocity to to something more realistic, or or whatever you want. But this is basically how you would specify that velocity of the car. But just for this activity, just so that we can see kind of the most deformation, I'm going to set the velocity to 150, which is going to be crazy. Right? Okay. And so, any questions on this so far? Okay. All right, so we're almost there, and so there's a couple things that we need to add, right? And so the first thing we're going to need to add is let's go ahead and define our solution fields, right? And so for this simulation, I'm interested in looking at the total deformation, and so let's go ahead and click total deformation, right? And remember, we're doing this by right-clicking solution A6, okay? And so let's look at total deformation. Let's look at equivalent stress. And let's also look at equivalent strain as well, okay? And so we should have three solution fields here. So total deformation, equivalent stress, and equivalent strain, okay? All right. And so that's the output fields. And then the last thing that we need to specify before we run the simulation is we need to specify the amount of time that our simulation is going to run, okay? And the way you're going to do this is you're going to click on analysis settings, right? And so if you look at, everything that we have here in the, in our outline, you can see that analysis setting still has a little question mark next to it. Right? And so this question mark, is a good indicator within Ansys that, Ansys wants you to input something here before we move forward, right? And so if you click analysis settings, you can see in the bottom left that the thing it wants you to input here is this thing called end time, right? And so that's the time that that you're going to end the simulation at. Right? And so, you want to set this end time such that you capture all the physics that you want within your simulation, right? And so you don't want to set this too short such that, it basically ends before the crash actually happens, right? And so you don't want to set this thing to be too short, but you also don't want it to set, you also don't want it to set it to be too long either, right? Because if you set it to be too long, and so say you set this to be 10 minutes, right? What you're going to be simulating basically is the car is going to hit the wall, and it's just going to sit there for 10 minutes because you decided to run it for 10 minutes, right? And then for that entire time, your computer is going to be running, Ansys is going to be running, and your computer is going to be very upset with you because it's going to be doing a bunch of work for nothing, right? And so you want to set it kind of at the sweet point where you capture all the events or all of the physics that you want to capture, but you don't set it to be too long so that your computer is kind of churning for nothing. 6 hours. Don't do that. That actually might blow up your computer. I'm just kidding. No, it won't. Okay, and so for an impact problem like this, impacts happen really quickly, and so we don't really have to set a lot of time for this. And so for this impact, we're going to set the end time to be 0.00075, so 3 zeros and 75 seconds. Okay, in other words, 7.5 times 10 to the minus 4 seconds. Right. And so we don't really need much more than this because, the impact is going to happen really quickly. And then, that's it. Okay. All right. Question. So does Ansys automatically assume the initial distance between the car and the wall? Yeah, that's a great question. And so Ansys is going to go based off, based off the CAD model directly. And so you can see here that there's basically no distance in between them. And so it's going to assume that there's no distance. When we run the simulation and we look at the animation, it's going to look like there's some distance in between there, but that's just something that Ansys does just for rendering purposes, just to kind of emphasize the fact that it's impacting the wall. And so what you'll see in the end is kind of just a rendering trick, just to kind of make it seem like the car is actually moving a distance. But in reality, there's actually no distance in between here. So we're going to be simulating right from from impact, basically. Yeah, and so if you want to do an impact problem for your project, and I know some of you are interested in doing it, you want to make sure that your two parts of your CAD model are basically kissing each other, and so they're right next to each other, so that there really doesn't have to be any distance that has to travel, and so it can just go, it can impact, and you can see kind of the results of that simulation right away. Yeah. All right. Oh, and also, the whole thing where we were doing the meshing, where we meshed very carefully the region of the simulation that we're interested in, and we coarsened up everything else. That's a good tactic for your project as well, because what tends to happen for your guys' final projects is that you guys are going to be working with some fairly sophisticated and complex CADs, but most of the time you're only really interested in the simulation results for just a small region of your model. And so a good tactic would be to really refine the mesh in that area, and then just really coarsen the mesh everywhere else. Okay. Okay. Oh yeah. Mm-hmm.
What is the number of steps and the current step number kind of do when it comes to the simulation?
Yeah. So that's a good question. And so the number of steps, these are all kind of internal settings that Ansys needs to run the simulation. And so basically what's going to happen is that for every time step or every frame that we're going to simulate, Ansys needs to solve basically a separate finite element problem. And the way it does it is slightly different than how it does it for kind of a static case. Just because we're doing unsteady problems, it has to solve it slightly differently. And so this number of steps, I think what that defines is, how many times do you want to kind of iterate within that one time step in order to get an accurate solution. And then the current step number, that's kind of just the starting step number. And so usually you usually want to start from step 1, and so that's usually fine. And so you can see there's a ton of settings in here, and so to really go over everything would take quite a bit of time, and it would kind of also require kind of a separate class in it. So for most cases, you can leave these on the defaults and they'll be okay. But a lot of these are kind of like internal settings for how accurate the simulation is going to be. Yeah.
Cool.
Mm-hmm. All right, question. So on top of solve cores, where is that? Solve.
It's at the very top on like.
Oh,
so there's solve and then cores. So if we bump that up, will that make it go faster?
Yeah. Yeah. So so what Josh is referring to is that if your computer has a multiple cores, and so like say you have a quad core processor, you can increase this number here to make it go faster. And so you can kind of almost think of it as like assigning more cooks to a problem, right? Or more hands or more workers to a particular problem. And so this is particularly relevant for dynamic simulations because it is so expensive. And so if you know your computer has quad core, you can bump this up to like 4 or something like that, right? If you want, and it'll make it go a little bit faster. Yeah, but you should do this according to your computer specs, and just be a little bit careful too that the default is 2, because I think most laptops are quad core, and so if you use up every single core on your system, say you change this to 4, then literally every single part of your CPU will be dedicated to running the simulation, and everything else on your computer will lag, and so you can't use Chrome, you can't watch YouTube videos or do other stuff, and so you can crank this up, but just be careful that it's it'll be hard to use other parts of your computer at the same time. Yeah.
Cool. Thank you.
Yeah. Got to download more cores. That joke has been made in every single one of my computational classes in this semester. So I'm teaching this class 417 and 442. Everyone's like, just download more cores, just download more RAM. It's I wish we could, but it's unfortunately it doesn't work like that. Okay. I should have clicked solve while we were talking because it's going to take a while. Okay, so with everything set, and so you set the end time, you set everything good, and so let's go ahead and click solve. And this is the part that's going to take a little bit of time. Right. All right, and so you can check the progress of your simulation down here in the bottom left, and so you can see mine is 5% complete. Okay, and now we kind of just have to kind of wait for it to finish. Right. So hopefully this doesn't take too long because I set the mesh elements to 16,000, but if you had a finer mesh, yours might be going a little bit slower. Okay. And if you want to see kind of a cool visualization for your simulation, instead of just looking at this, which is kind of boring, what you can do is you can click solution information right here, okay, on the left-hand side, and that's going to give you this. And so this will kind of tell you, what's going on underneath the hood. But this is useless right now, and so this is kind of just random text. And so let's change this solver information. Right? And so for those of you guys who crank this up to 4, it might be difficult for you to do this because your whole computer might be dedicated to it. But if you can, you can click solution information, and then from here you can change it from solver output to energy summary. Right, and so what you're seeing here is the different amounts of energy that are propagating throughout your simulation, right? And so let's look at kind of the left side of this graph right here for kinetic energy, right? And so you can see at the very beginning of the simulation, kinetic energy is at a high, right? Because all the energy in our simulation is going into the motion of the car, right? So remember, for our initial conditions, we set an initial velocity of 150 meters per second. And so all that energy is kinetic, okay? And so that's that's good. But then once the car impacts the wall, right after the car impacts the wall, its velocity drops, very rapidly because it's hitting the wall and it can't move, right? And then as the car hits the wall, to kind of because of conservation of energy, that kinetic energy gets converted into energy that's going to crumple the car, basically, right? And so you can see as the kinetic energy goes down, our internal energy goes up, right? And so that internal energy represents the energy of the car that's basically crumpling in front of our eyes, right? Okay. And so usually, you know, for most realistic simulations, it would end right here. And so the car would hit the wall, and then its kinetic energy would drop, and then its internal energy would rise, and the car would end up, you know, mangled or deformed. Right? But you can see something interesting is happening because, you know, these graphs are kind of oscillating like this. And the reason for that is, you know, because we assume, you know, we assumed basically that our material was perfectly elastic, right? And so remember, we assigned aluminum alloy. And so we basically assume that our stress strain curve is perfectly linear. And so what's going on is that we're kind of having a spring effect where the car is hitting the wall. And then because our material can't buckle and it can't deform, it's basically going to hit the wall and kind of spring back. And it's going to keep kind of doing this kind of back and forth. Is it indicating multiple impact? It's not really multiple impacts. It's kind of more like you can almost think of it like a big spring. And so if you took a spring and you kind of rammed it into a wall, then the spring is going to go kind of like do this kind of accordion thing, where it's going to go kind of go like back and forth like that, right? And so it's going to basically slingshot in between kinetic energy, internal energy, kinetic energy, internal energy. And you'll kind of see how that is, you know, once I play the animation. Okay, and so once the simulation is done, you can go ahead and click on any of your results. And so let's look at equivalent stress. Okay, and so you can see here, this is I think this is the ending result of the internal stress of the equivalent stress right here, right? And so to play the animation, you want to go to the bottom center of the screen and you want to click on this play button right here. And so you can see you know, the collision happening right here, right? It does look like jelly, yes, yeah. And so, you know, unfortunately, you know, because we assume just kind of linear structural dynamics, and so there's basically no buckling. The material is basically going to act like a perfect spring, and so it's going to impact the wall. It's going to spring back, and it's going to spring. You know, it's going to basically do kind of like a, you know, just like a spring would. Right? Yeah. So the animation is down here on the bottom of the screen, and so you should see a bar here called animation, and you can go ahead and click the play button on that one right there. Yeah, and so in order to view that, you might have to click on one of these result fields, right? And so I click on equivalent stress. You can either do equivalent stress, equivalent strain, or total deformation. All of them work. And then you need to click the play button, just like that. Okay. All right. And so yeah, it looks like Jell-O, and it looks like kind of a wiggly thing. It's because, you know, we assumed our material was perfectly elastic, right? But if we chose like a nonlinear material or a buckling material, then, you know, the car would actually deform and it would stay like that. Question?
Is there a way to like slow down the animation so we can see like how the deformation goes through the rest of the body?
Yeah. So I think the way you can do that is you can click on this menu right here. So right now it plays the entire animation in 2 seconds, and so let's change this to 10 seconds right here. And let's change this to 100 frames over that 10 seconds. So I think you can play this one. Oh, my computer is blowing up.
Sorry.
There we go. That's fine. Yeah, I guess 100 frames is too much for this one. But yeah, I think that's how you slow down this animation, I think. Let me see. What happens if we do that? Yeah, so I think if you change this to 10 seconds right here, then it would then it kind of slows it down just a little bit. Mm-hmm. Yep. All right, and so that's the that's the activity. Okay. And so from here, you should be able to do, you know, everything in the problem set, right? And so the main thing I want you guys to focus on for this activity is problem 5. And so the problem 5, what I want you to do is to find the maximum velocity that the car can do to you know, before so it can hit the wall and still be in one piece, right? And so in problem 5, I gave you the maximum yield strength of the aluminum, which is 55 megapascals, right? And so you can see here that the stress is way higher than 55 megapascals, right? Which makes sense because, you know, we basically shot this car at the wall at the speed of a bullet. And so, what I want you to do is I want you to play with this velocity here and find the maximum velocity that the car can travel and hit the wall and still be okay. All right. And so that's your task for problem 5. And then for problem 6, what I want you to do is to change the material of the car from aluminum to plastic and repeat kind of the same thing. Okay. And so for plastic, it's obviously has a much lower yield strength. And so the velocity that the car can go to hit the wall is going to be much, much lower than that. Okay. All right. And so I'll let you guys do those parts on your own. And besides that, that's all I had planned for this activity, right?
Professor, I had a couple questions.
Yeah. What's up?
So if we were to click on like total deformation, the equivalent elastic strain, or the equivalent stress, without playing the animation, what does the static version represent? Is it like where and when does these stresses being applied?
Yeah, and so this is basically the last frame in the animation right here, and so you can.
Oh, the last frame. Okay.
Yeah, and so you can see kind of this black bar right here, and so this kind of shows you where that is, and you can pause this animation anytime too. And so let's go ahead and play it. Yeah, and so you can basically pause this animation basically whenever you want.
I see.
Yeah.
So
yeah,
then, sorry, go ahead. My other question was, sorry, wait. Sorry, I was playing it and I forgot my other question. I'll come back to you.
Okay. Yeah. All right. And so we still have 15 minutes of class left, and so I'll stick around if you guys want to play around with this a bit, or if you have any other questions. But if you if you want to head out, you can definitely feel free. So thank you guys for coming in today. Hopefully, this activity was fun for you guys. For me, this is my personal favorite activity, just because we get to crash a car into a wall, which is usually frowned upon if you do this in real life. And so doing this in animations is kind of fun, right? And so this activity is due in 2 weeks, and so it's going to be due on the 23rd. And so that's around the time when we're going to do our next activity. And so you have a bit of time for this one. If you have any questions about it, definitely, don't be afraid to reach out. So hope you guys have a great weekend. Don't forget about your proposal. So that's due tomorrow, right? And I'll see you guys next week.
Okay, I got a quick question.
Yeah, what's up?
So finding the, sweet spot for the velocity impact. What's the best way to do that? Just pick a number and then try another number.
Yep.
And narrow it down. There isn't like an iteration that we could do automatically.
Yeah, that was going to be actually my question, was can we do like for loops within Ansys and then just have it run for a couple hours or something?
Yeah, so you for this one, I think there's a way to script within Ansys, but for this activity, I kind of just had in mind just to kind of try different ones and then go with that. The whole thing is linear though, and so if you can see here that we got a stress of 3.3 e to 9 with a velocity of 150, and so let's go ahead and reduce this by half, and then the stress should reduce by about half as well. And so you can kind of use that as kind of a it's not going to be exactly the same as half, because there's it's a dynamic problem, but it should give you kind of a good benchmark. So if your target is like 55 megapascals, and so and we get 3.3 times 10 to the 9th with 150 meters per second, and so you can kind of use that and assume a linear relationship to find that right velocity.
Okay, my other issue was the proposal. I've made a decision as to what I'm going to do, but I kind of want some advice on how to approach it, because I think I'm going to make this the graduate design project for me as well.
Okay.
And I'm going to go with the submersible window.
Cool.
And the mating surface between the two, between the acrylic and I think I'm going to do aluminum for the body.
Okay.
And there's got to be like a rubber gasket in there. I understand what basic behavior needs to happen for it to not fail. But I think what I'm wondering is, what's the best approach for figuring out everything from the design materials to, or the properties of the materials to the dimensions and all that.
Yeah. So the kind of the first thing that I would approach it with is kind of just as like an iterative approach. And so if you look at, what kind of materials that you have available for all the different parts and kind of just make a list of those, you can run a simulation with, all the different combinations of materials and see, which one works out. And so that works for the materials. In terms of the construction design, later on in activity 6, we're going to use a feature within Ansys called topology optimization. And so what that does is it basically, you would present Ansys with basically a structure and with some loading and constraints, and then Ansys will basically help you to find a more optimal geometry that kind of cuts away a lot of the unnecessary material that you can.
Okay. So like it could be flatter if it's thicker around the edges. Right. Or that sort of thing.
Yes. Yeah.
Okay.
Yeah. So the topology optimization will help you out with that. But kind of just based on the besides that, kind of based on what we've learned in this class, kind of the best approach would just be to iterate. And so you would run a simulation under a certain configuration, and then from there you would say, okay, maybe I want to thin out the geometry here, or maybe I want to try a different material here, and then make those adjustments, and then run the simulation again, and then go based on that. There's some automated tools like the topology optimization, which we'll learn. But a lot of it's going to be largely iterative on, different stuff that you're going to try manually.
Yeah. Okay. For the proposal, a picture of what it is that I'm going to do, or would a sketch work?
Yep. A sketch is fine. Yeah.
Okay. And then just what do you want me to say? Just describe what I'm approaching at, or what I'm going to do.
Yep.
What's my approach? What I'm trying to accomplish.
Yep. So basically the
like a paragraph.
Yeah. So basically the conversations that we've had after class, just basically write it up in a document, and I'll give you more careful feedback on the proposal too. So beginning of next week, I'll be going through everyone's proposal, and I'll be giving some comments on, just advice on how I would approach it, or maybe ways that we can formulate it to, to make it a success. Yeah.
Okay. Thank you.
Yep. All right. Okay. So it was so we ran it with half the velocity, and so actually the stress actually reduced by quite a bit. And so yeah, and so one better way to start would be to put a more realistic velocity here. And so instead of 75 meters per second, which is insanely fast, let's do maybe like 40 miles per hour. So 40 miles per hour is about 18 meters per second. And so let's go ahead and change that. Right, and let's go ahead and run the simulation again.
Professor?
Yep.
For the project, if we have a system that is symmetrical, how would we, I guess, cut our system in half to do the actual analysis?
Yeah, that's a good question. I think probably the easiest thing would be is to go into a CAD software like SolidWorks, and then manually cut your thing in half there. I think that would probably be the easiest thing to do.
Well, even if it's an assembly, not if it's like a single part, just cut it in half, even if it cuts a part in half.
Yep, that's totally fine, because if it cuts the part in half, what you can do in Ansys is you can apply like a symmetry boundary condition there.
Oh.
Yeah.
Okay. Sweet, thank you.
Mm-hmm. It's been a while since I've used SolidWorks, and so I'm not sure how you would actually cut the part in half, but it happens all the time in engineering, because so you have symmetrical parts all the time. And so I imagine that there's some functionality in there to cut it in half. But once you do, then throwing into Ansys is simple, because then there's built-in symmetry boundary conditions that you can do. And so actually I can, well, after this finishes, then I'll show you the symmetry boundary condition.
Dr. Chen, is it not possible at all to do quadratic on this simulation?
It is possible. I mean, realistically, there's nothing stopping you from doing it. I think it might be a limitation of the academic version of Ansys. And so you can try it, but I remember when I tried it last year, I couldn't get it to work, and I kept getting errors from it. I haven't tried it here today, so it might be worth trying.
I just made my mesh like really coarse, and it's still not liking it.
Okay, yeah. I'm not sure if it's something that they just prevent just entirely because it's a student version, but theoretically there's nothing stopping you from doing that, and there's a lot of applications that do use quadratic elements for dynamic simulations. I think it's just a feature that they hide for the academic version. That's what I'm guessing.
Gotcha. Okay.
Professor?
Yep.
Could I run a project idea with you?
Yeah.
So my brother and I, we've been working on like a land drone chassis.
Okay.
So I was working on it yesterday, but I haven't had time to actually add the wheels and everything to it. I just have the chassis.
Okay.
So would it be a viable project to just like figure out how much load it could take before it would like break, or
yeah, that sounds
could take?
That sounds like a perfect project. I mean, that's a problem that you're personally interested in, and something that you obviously don't want to destroy your chassis to find out, and so it's perfectly.
I just didn't know if that was
simulation.
too simple. Okay.
No, that's perfect. And so, I think the complexity, I think for you, probably be in meshing it, because I think that's the thing that most people struggle with, is that you have this fairly complicated CAD, and meshing it to the right way and getting it to fit within the student version. I think that's going to be the main challenge for most people. And so, yeah, no, I think that's perfect.
Okay, thank you.
Mm-hmm. All right, and so we're getting a little bit closer here, and so just go ahead and keep reducing the the velocity until you reach something that's less than 55 megapascal. Yeah.
Sorry, Professor, I'm back. I didn't know if you already did this symmetry thing or not.
Oh no, not yet. I was waiting for it to finish. All right.
Gotcha.
And so let's do this. Okay. And so the way you apply the symmetry boundary condition is kind of the same way as you would do a support. And so let's see. Usually there's something here. Maybe it's not available for dynamic simulations, but there usually is like a symmetry option here. But even if there's no symmetry option, like we've already learned in the class how to apply symmetry, right? And so let's say that this wall right here is going to be a symmetric boundary condition. And so remember, for symmetry, we basically want to apply a roller constraint on this wall, right? And so the way that we would do that is we would insert a displacement constraint, and we do it on this surface right here, right? And if we had another wall that's symmetric on this side, ignoring the car, but let's say that wall is doubly thick, we want to make sure that we don't have any displacement in the x direction, right? And so we do 0 like that, and so that prevents any displacement into this plane or out of it, and then we'd be able to apply our symmetry condition that way. But I think if you're doing a static simulation, there's an explicit symmetry boundary condition here. I think it's just not here because it's a dynamic simulation. Yeah.
Gotcha. I see. Okay.
Okay, so for our project proposal, do we have to include like a diagram for what we're doing in there? Because
if you have like a picture of the CAD, or just like a drawing that you can do that just to give me a sense of the geometry that you're going to be working with, because I would like to see it, because a lot of times the CADs end up being pretty sophisticated, and I make comments of maybe we should simplify this CAD a little bit just to make sure that we can mesh it, because a lot of times the CAD ends up being more complicated than we can mesh in Ansys. And so if you have a picture of the CAD that you can show me, that would be great. But if you don't have that, and you have just like a sketch that you can give me, then that would be great as well.
Dr. Trent?
Yeah, what's up?
I'm having an issue because on mine it's like the car's stuck to the wall.
Did you
it's attached.
Did you remove the contact here?
Contact. Let's see here.
So if you go to connections here on that line, and then
Okay.
you might see like a plus arrow here for the contacts. And so if you what we want to do is we want to delete the contact between the wall and the car.
Contact region delete.
Yes. Yeah. Just delete it. Yeah.
Okay.
Yeah. So if you run the
think that might have
simulation
been
now, then if you run the simulation now, then the car should bounce off the wall just fine. Yeah.
Oh, I think that's what it was. Sorry. And then also another question: if we're going to work in teams for our project proposal, do we just turn in one, or do we each turn in the same one?
Just turn into one. That's fine.
Just turn in one, and then the other person's name will be on it, and then
Exactly.
you'll know.
Yeah. Yeah. And I'll give you credit for both of them. Yeah, for both
Perfect.
of you guys.
Perfect. Thank you.
Yep.
Professor?
Yep.
In terms of so for my project, I'm doing my senior design, and I was wondering, like, it's a multi-component system, but I'm really only concerned with one of the components, like in its failure criteria.
Yep.
So when I do the simulation and the modeling, like it technically is like loading on like the whole system, but then it all transfers to one part. And so like would I still just include the entire system in Ansys and then just hide it all, or just only do the one part and apply the loading?
Yeah, that's tough because the most accurate thing would be just to do a simulation of the entire system. What you can do, because it's how that load transfers to that one component is often kind of difficult to determine, and so we need to perform a simulation on the entire thing in order to get that correct. What you can do though is that, since you know what component that you're interested in, you can make that component have a really refined mesh and have a fairly coarse mesh everywhere else, just to make sure that you can run the simulation. Yeah.
Okay. And then other than that, I have like for that singular part at different stages of its life, it has different loadings, because it's basically a plate on our airframe that holds up like the wings and the landing gear and some other things. And so, it could be under like impact loading from landing, or it could be under stresses from like wing bending, or like any number of different aerial or aerodynamic forces. So I was just wondering, like, how would I distinguish between, because at different times it'll be different loadings, like how would I distinguish that?
Yeah, you can just do separate simulations, and so you can do a simulation for landing, you can do simulation for the wing loads and stuff like that, and so you can do each one as a separate simulation and then kind of present each of them in your report.
Okay, perfect. Then I think I'm good to go. Thank you.
Okay. Yep. All right, so it's 5:15, and so does anyone have any last questions before I run off to my next lecture? All right, Manuel and Simon, I guess I'll see you in 4:42 next, and so I'm going to go ahead and switch over to that one. Okay.